Okay, let's do an example. Let's actually solve a forced harmonic oscillator. And before we do that, I do want to review the extended linearity principle, which says that if you're trying to solve this non-homogeneous or forced equation, all you have to do is find the general solution to the homogeneous version and find any particular solution to the forced equation and just add those together and you'll get your general solution. So that's exactly what we're going to do. So to solve a forced harmonic oscillator, let's write those steps down. You're going to solve the unforced equation, get the general solution. You're then going to find any particular solution to the forced equation, which sounds really easy, right? You have to find every solution to the unforced equation, but that's actually pretty easy. But then finding any solution to the forced equation actually can be hard. And it won't be that hard for us because I'm going to give you nice equations. But if you don't get nice equations, it's either hard or impossible. So this is really the kicker a lot of times. And you just add them, and that's your general solution. That's it. Just 3 steps, just like 1.8. I keep saying just like 1.8. This really might be a good time, if not a few hours ago, to review your notes from 1.8. What did it look like to solve linear differential equations first order with constant coefficients? Because really, this is the same thing. The only thing that's different is solving the unforced equation. But we have chapter 3, so we can do that no problem. Okay, let's give you an example and use this step-by-step process. The example we have here is y double dot plus 5y dot plus 6y equals e to the negative t. So we can pause here before we start and really think about what this could represent. This could just represent a generic differential equation. This could have no meaning whatsoever. Or we could see it as a forced harmonic oscillator. We could see this as a mass moving on a table, right? Maybe we have a table with a mass attached to some kind of spring that's attached to some fixed object, right? And maybe there's a force being acted on this mass, and it's an exponentially decaying force. We know that the ratio of the spring constant to the damping force in the mass is 5. We know the ratio of the spring constant and the mass is 6. So you could see this as a mathematical object, or you could see it as representing a physical situation. And we know from the previous video about those qualitative implications that our solutions are going to behave long term like the particular solution, which might make us think that our solutions long term are going to behave kind of like this. But we'll see what we actually get, and we'll have some cool pictures on Desmos as well. Okay, so let's solve it. How damped do you think this is? We'll find out. Remember, if B is relatively large, or in this case, if P is relatively large, it'll be overdamped. If it's relatively small, be underdamped. And if it's in that sweet spot, critically damped. Okay, let's get solving. So we need to find our homogeneous solution. First, we have to solve this equation. Pretty much the same thing. Just let's forget about the forcing. Let's say there was no force. What would we do? Well, you could solve this a lot of different ways. You can convert it to a system, find the eigenvalues and the eigenvectors. Or you could remember what we did in the last section, well, not last, the penultimate, 3.6. And we could say, let's just guess. We think the solution's going to look like e to the st. And when we plug that in, the second derivative of that is s squared. E to the st. The first derivative is s e to the st. And then we have 6 e to the st, and that all has to all equal 0. We get the characteristic polynomial equal to 0, and we can factor that, I think. Yes, we can. Because we give you nice problems in this class. For now. The last example of this section does not have quite so nice of numbers, but it is good practice to see what happens when the numbers don't look nice. Because again, thinking about physics and thinking about engineering applications, the real numbers aren't nice. And really we approximate a lot of times. Math professors don't like to approximate, but we have to. And in applications, yes, people approximate all the time because you can never find an exact measurement. You measure something to be 2.5 inches, it's not actually 2.5 inches. It's 2.5 inches within some tolerance level, right? Anyway, I'm getting distracted. We found our eigenvalues are 2 and 3, and we know what our solution is going to look like. It's just our general solution to the homogeneous version is going to be k1, -2. Whew, I cannot factor. -2 and -3. Otherwise, it wouldn't be stable. Right? Our equilibrium needs to be stable. And again, we see that these are real eigenvalues and they're distinct. So we know that it's a stable node specifically. It's not a stable spiral. We don't have an underdamped. This is an overdamped system. Well, if the homogeneous one is an overdamped harmonic oscillator. So then we know that our answer is going to look like any solution to this overdamped harmonic oscillator is going to look like this, plus k2 e to the -3t. So now that we have the general solution to the unforced version, the homogeneous version, we need any particular solution to the forced version, the non-homogeneous equation. So just like we did in the past, we're just going to guess something. We're saying, all right, if I only have y's and derivatives and I need it to be an exponential function, I think my function's probably going to be an exponential function. So let's do that. We're going to guess maybe it's e to the -t, and maybe it's going to have some coefficient, any letter you want to use here. Maybe it'll look something like this. Well, if it does, what needs to be true? Then the left-hand side of our equation, and I should really start this on the next page, huh? Right, this is our differential equation, and if that needs to be true for us to have a solution, then the left-hand side, if we're guessing our particular solution is a e to the -t, left-hand side will be the second derivative of this, which is just a e to the -t, right? It's negative times a negative, okay. Plus 5 times the first derivative, which is minus a e to the -t, plus 6 times the function itself, which is a e to the -t. We just combine like terms. All of this is e to the -t, and we have a minus 5a is -4a, plus 6a is 2a. And that needs to equal the right-hand side for this to be a solution. Oh gosh, what did I do? Everything's fine. Because there's a 1 in here. E to the -t will always equal e to the -t, so we just need 2a to equal 1. So there's a solution when 2a equals 1. I know when that happens, when a is equal to 1/2. So we found our particular solution. Our particular solution was just 1/2 e to the -t. That's a solution to this differential equation. We've done all the hard stuff. We did step 1, we did step 2. We just add them together now. So our general solution to the forced harmonic oscillator, velociraptor, I don't know, is y of t is the homogeneous general solution, which was k1 e to the negative 2t plus k2 e to the negative 3t plus our particular solution 1/2 e to the negative t. And we can say some things. We can say that as time goes on, every single solution, because again, here is, right, this is the general solution. This is, how do you say it? This is our natural response. And this is our forced response. Well, eventually, all of them are decaying, actually. Our forced response is also decaying in this situation, but this will decay faster, right? They have bigger exponents. So this will decay more quickly, and any general solution will eventually approach yp, which is also approaching 0. And we can visualize that with Desmos. So what I did here is I plotted, let me move this a little bit. I plotted the general solution. And I said, let's be able to change K1 and K2. Now, we already know that no matter what K1 and K2 are, this blue curve, and the blue curve is our solution, this blue curve needs to represent an overdamped harmonic oscillator. So we should never get any oscillations. Kind of looks like an oscillation, but remember we said even overdamped things, if they have enough of an initial oomph, they can still overshoot equilibrium, but then they will come back to equilibrium and they won't oscillate. They can overshoot it once, but they won't oscillate. So you can see, again, we can change the constants and we still get that same overdamped situation and just changes like the beginning. And eventually it's approaching this green line. We change the other constant too, right? And you can see that, sure, it'll change things, but it's still eventually approaching that green line. What is that green line? Our particular solution, our forced response. And no matter what combination you choose, they'll all approach the green line eventually. And again, they're all going to 0. And that's what we've got going here. So just like in chapter 1, this method right here that we use to find the particular solution, this is called the method of undetermined coefficients, which is basically just guessing. And if you remember, our guess depends on the right-hand side. So if the right-hand side, coefficients, so that's right. If the right-hand side is an exponential, we're going to guess something that looks like an exponential. If the right-hand side, right, if g of t, let's make a little table, right? If g of t is an exponential, maybe we say e to the kt, we're just going to guess a times e to the kt, right? If the right-hand side is a cosine function, maybe cosine of kt, or sine of kt, or any combination of them, we're going to have to guess both. We're going to have to guess a cosine of kt plus b cosine of kt. We're going to need both sines and cosines no matter what it is over here. If you have an nth degree polynomial, we're going to be guessing an nth degree polynomial. And we'll give you some more practice on this. We'll do it a little bit in the videos, but mostly on the homework. And that's really the common guesses that we're going to get. We're not going to deal with anything super messy in this class. These are kind of the main things that we're going to look at. And again, as a reminder, this is to help us find any particular solution to an equation that looks like this. Notably, what do we have here? We have a linear second order differential equation, non-homogeneous, with constant coefficients. That is very, very important. And again, if we did it for a first order equation in chapter 1, and we did it for a second order equation here in chapter 4, can we do it with a third order equation? Yes. things just get a little bit more complicated. But that's pretty much it. We'll do another example in the next video and another example in the last one. The last video has a very special example, but should be fun, should be a good time. Hopefully it doesn't crash and burn. And if it does, well, that's content. Enjoy the rest of your day, enjoy the rest of your math, and we'll get into second guessing in the next video.